All right, welcome, Kirkwood School District, Sound and Light, 6th grade science. We're going to take a look today at our goal of describing the source of energy of all the things in our planet, as well as how that energy is transferred to the Earth in a range of wavelengths and energy level. That range of wavelengths and energy levels is called the electromagnetic spectrum. We're going to learn more about that today and check this information out. For example, when we're sitting there and just kind of hanging out, what are some examples of some waves or rays that are around us? Well, the list there are just some of the ones that you may consider to be waves that are around you. Everything from sunlight to visible light to X-rays to gamma rays. These are things that you might find as you're just sitting there. These waves are moving at what is called the speed of light, which is 300 million meters in 1 second. And to get an idea of what that's like, the light from the sun reaches the Earth in only 8 minutes. That's pretty impressive. There are times when it is probably easier for us to explain light as a stream of particles because of the speed and its properties and how it behaves. We typically draw light in the form of a ray. So you can see a ray here with an arrow pointing at one end and a point of origin, which is the source. Now, if I were to ask you a question, where does all of the energy of Earth come from? I would hope this source that you're thinking of would be the sun. All right? Now, this light that we sometimes see is polarized and can be polarized because you can get what's called a polarizing filter, and that's sort of the big deal in sunglasses these days, that can eliminate some of the wavelengths of light to only allow certain wavelengths through. When that happens, we can polarize light, and we can only take a certain amount or certain wavelengths to enhance our vision. All waves, I shouldn't say all, most waves have these two things in common. One, they transfer energy from one place to another. Two, they require a medium. Now, the reason why I say not all waves is because, as we've discussed, if you take a look at that second one, they require a medium. Light, for example, does not require a medium. So these are things that all typical waves have in common, or sound waves have in common, or an ocean wave have in common, but not all waves have this in common. We're going to take a look today specifically at electromagnetic waves, and we're going to review a couple of concepts here. Electromagnetic waves are transverse waves that have properties those of electrical and magnetic. So electromagnetic waves are special because they consist of changing electrical and magnetic fields. And remember back that transverse means that the medium is moving perpendicular to the direction of the wave. So as the slinky in this picture moves up and down, the energy of that slinky is moving from this side over to this side. Okay, perpendicular. The electromagnetic spectrum is the name for a range of electromagnetic waves placed in order of increasing frequency. Okay, now this is going to be an important concept that we go back to discussing wavelength as well. As we increase frequency, what happens to the wavelength? Let's take a look at this picture here to make sure we understand this and everything else past here makes sense. First of all, as we increase frequency, that means we're going from this area over to this area. Look at what happens to the wavelength. Notice that the arrow of increasing wavelength is pointing in this direction, when the arrow for increasing frequency is pointing in this direction. You'll notice they're opposites, and that supports what we've already discussed when we looked at the properties of different waves. So as the frequency increases, the wavelength decreases, okay? And as I go from this area over to here, I see that the wavelength increases from here to here, Okay? But at that time, the frequency goes from very high to very low, and we'll show you that as we go through here. So here are all the waves on the electromagnetic spectrum. We're going to look at every single one of these today. Radio, microwave, infrared, visible light, ultraviolet, X-rays, and gamma rays. Okay? This is a great video to get us started to take a look at the electromagnetic spectrum. So I'm going to load that up, let you watch that, and I'll be back with you.
Spectrum, an immense scale we use to measure the wavelengths of all kinds of radiation. At one end are radio waves with the longest wavelengths. At the other end are gamma rays with the shortest. In between are the other bands, including visible light, which is such a tiny fraction of the whole, it's difficult to imagine. How small is the visible spectrum? If you had a reel of movie film representing the entire electromagnetic spectrum, stretching 2,500 miles from California to Alaska, the section containing the visible spectrum would fall somewhere in the middle, near the University of Washington.
This frame is the whole visible spectrum. It is one frame and over 2,000 miles of tape, and it's everything that the human eye can see. The importance of this frame is that stars emit almost all of their light in this part of the spectrum.
And even though the light is visible, it still contains hidden tools. The secrets are in the spectrum itself. The visible light in this lamp comes from hydrogen gas excited by electricity to form a glowing plasma, similar to what happens in a nebula. By viewing the lamp through a diffraction grating, we can split the light up into 3 narrow lines on the spectrum, a virtual fingerprint of light, unique to hydrogen alone.
So in the spectrum, you see 3 features. One is red, one is a light blue, and the other is a deep blue. This pattern of wavelengths is absolutely unique to hydrogen, and there's no way to confuse hydrogen in the spectrum with any other element.
The first kind is called radio waves. Radio waves are electromagnetic waves with the longest wavelength and the lowest frequencies. Remember, those two things are opposites, wavelength and frequency. So these have the longest wavelength and the lowest frequency. They include broadcast waves for radio and television, and also a little bit about microwaves, and we're going to look at that next. Microwaves are just simply radio waves that have the shorter wavelengths and a little bit higher frequency. So we're going to start seeing that the wavelength is going to start getting shorter and shorter, and the frequency is going to get higher and higher. Okay? Infrared rays are invisible heat waves that you feel, which is called infrared radiation or infrared rays. Wavelengths shorter than those of radio waves is what they have. So take a look at this picture. Here's infrared. You've got radio down here. You've got micro. And then you have infrared. And then within that infrared, notice there are things like sunlight. Sunlight is the #1 producer of infrared rays. And a lot of that heat that you feel from the sun is basically IR or infrared rays. Now, of all of those, which of those can you see? All the different waves of light, the wavelengths of light, you can only see a very small part, and that's called visible light. Why can't you see the others? Well, the waves are moving either too fast or too slow. Or the wavelength is too short or too long for your eyes to be able to pick them up. White light is composed of multiple colors of light. Red has the longest wavelength and bends the most. Violet has the shortest wavelength and bends the least. Ultraviolet are electromagnetic waves with wavelengths just shorter than visible light, so we can't see them, and they're called ultraviolet rays. you know them best as UV, ultraviolet, UV. Ultraviolet rays have a higher frequency than visible light, so they carry more energy. The energy of ultraviolet rays is great enough to damage or kill living cells. That's why you put on some sunblock when you go outside to protect against those ultraviolet rays. X-rays here's Homer Simpson. X-rays are electromagnetic waves with wavelengths just shorter than those of ultraviolet. Their frequencies are just a little higher than ultraviolet. But because of their high frequencies, X-rays carry more energy than ultraviolet. And these can go past the skin and penetrate most matter. Dense matter, such as bone or lead, absorbs the X-rays, but does not allow them to pass through. So that's why the X-ray can go through your skin, through your muscle, but still stop and sort of show that outline of what that bone, the more denser material, is. Finally, the most powerful, the most amazing, the most ridiculous is gamma rays. Gamma rays have the shortest wavelengths and the highest frequencies. Because they have the greatest amount of energy, gamma rays are the most penetrating of all the electromagnetic waves. So you can imagine that if ultraviolet damages your skin, X-rays goes through your skin, but stops at your bones, what do you think gamma rays can do? They can be pretty harmful. Two questions to kind of wrap us up and take a look at this goal and ensure our understanding. In what ways are all electromagnetic waves the same? Well, all electromagnetic waves travel at the same speed. In what ways are they different? They have different wavelengths and different frequencies. As the wavelengths of electromagnetic waves decrease, what happens to their frequency? Remember, this is an important concept, that wavelength and frequency have an inverse or an opposite relationship. What happens to their energy? Well, the amount of energy carried by an electromagnetic wave increases with the frequency. So the higher the frequency, the more energy it has. And we knew that and we figured that out when we talked about ultraviolet, X-rays, and gamma rays. Our goal today was to recognize and be able to describe the source of energy for everything here on Earth and how it is transferred to the Earth in a range of wavelengths called the electromagnetic spectrum. We've got a ridiculous but fun song to wrap up our show here today in our video. I hope you enjoy it. I think it's ridiculous and I think it's fun. Have fun.
Mr. Worldwide, C-Paul. So listen up. Here we go. Electromagnetic spectrum. Here we go. Electromagnetic spectrum. Here we go. Electromagnetic spectrum. Here we go. Electromagnetic spectrum.
Radio waves, what's on TV tonight? And microwaves, they will cook your popcorn. From body light that's infrared comes from you and me. You can see visible light colors galore. Not shady ultraviolet rays can give you a suntan, and then X-rays look at phones if you want. And there be shortest of them all are the gamma rays. Altogether it's the EM spectrum.
Radio radiation. Electromagnetic spectrum. Radio radiation. Electromagnetic spectrum. Radio radiation. Electromagnetic spectrum. Radio radiation. Electromagnetic spectrum.
Ooh, it's all radiation, make me wanna say it. Yeah, you can group them all, make me wanna say it. Ooh, you got it, radio to gamma rays. Yeah, don't stop it.
Electromagnetic spectrum. It's radio waves, microwaves, infrared, visible. It's ultraviolet, X-rays, gamma rays. That's the way. Electromagnetic radiation. Let's talk about. I want you to chat about energy. Now let me see the spectrum, baby. Chat.
Radio waves, what's on TV tonight? And microwaves, they will cook your popcorn. From body light that's infrared comes from you and me. You can see visible light colors galore. Not shady ultraviolet rays can give you a suntan, and then X-rays look at phones if you want. And there be shortest of them all are the gamma rays. Altogether it's the EM spectrum.